So as I was getting ready to kick off Gen Chem 2, it's kind of neat how hopefully you'll see where it shakes hands with what we talked about in Gen Chem 1, which should be the case, right? So, for instance, in Chem 1, we talked about chemical bonds, okay, but I don't want to put anybody to sleep. It's not that will shake hands, because we do diverge here in a minute. But we talk about chemical bonds where atoms are bonded together. That bond can be a covalent bond or an ionic bond. And if the bond is covalent, electrons are shared. Remember, anytime on a Lewis structure you see a dash, think 2 electrons? Okay, electrons are being shared. That's exactly it. So that's a covalent bond. By the way, Lewis structures are, hopefully you'll remember how to do them. You need to brush off your cobwebs on drawing Lewis structures. So, but another thing we need to talk about right off the bat is this idea of electronegativities. So if you have atom A and atom B that are bonded together with a pair of electrons, remember that if one has a higher electronegativity, the symbol for electronegativity is that Greek chi, looks like an X, kind of a fancy looking X. Okay. The one with a higher electronegativity will pull electrons more of its lion's share. It will have the lion's share of electrons drawn to it. So electronegativity looks like this. So if this is your group A elements, do you remember how electronegativity works? Which way does it increase? Does it go from left to right increasing, or from right back to left increasing? Very good. Yep. Increases. Very good. What about the group? Increases going up? Yep. Exactly. So we don't have a periodic table in here. Oh, I think I'm going to have to bring handouts of periodic tables. But if you have carbon bonded to oxygen, which one's more electronegative? Oxygen's more electronegative. Okay, and hopefully this is ringing some bells. So this one has the higher chi. So electronegativity is greater than this electronegativity. So that means that this is going to be negative, right? But we use these lowercase deltas. We're actually going to see this in the PowerPoint slides. The lowercase delta looks like this. It looks like an S with a little kick on it. So that means partially negative. And this is partially positive. We good with that? All right. This that I'm describing, the partially negative and partially positive, that is called the polarity of the chemical bond, the covalent bond. All right. Electronegativity, Greek letter chi. Electronegativity, you told me, increases from left to right for the group A elements across the period, and it increases for group A as you go up the group. And it is a measure of electrons being attracted to an atom that's bonded to another atom. All right. So the higher the electronegativity, the higher there is, or the more likely that atom is to attract electrons to it. So here in a minute, you're going to actually see, and I think we saw these before. I'm going to erase some of this. It's kind of messy. Greater electronegativity. If I were to look at kind of the buzz of electrons, I would make the buzz of electrons small here, and I would make the buzz of electrons big over here. That kind of cloud, that's kind of where that's like the electron cloud. More over here, smaller over here. So you already told me this. Electronegativity for group A elements. Go that way increase, that way increase. Here's one for you. When you're drawing a Lewis structure, which one do you put in the center? The higher electronegative or the lower electronegative? How many people think it's the higher one? How many people think it's the lower one? It is the lower one. Very good. Lewis structures. So these are kind of the electronegativity values. I don't know if you remember electronegativity values we call Pauling values, they mean the same thing. But it's hard to kind of judge, how tall that is. High electronegativity, low electronegativity, and electronegativity increases as you go up the group. These are also the Pauling values, the electronegativity values. Again, much easier to see. And I actually printed off a copy of this for me. So if you want to dog-ear that, I'll probably come back to that here in a minute. So it's nice and easy. Sometimes it's hard to see how little, tiny. Oh my gosh, you can't see those. Anyway, your OpenStax book, figure 7-6. Okay. So I said that kind of as we have this partial negative and partially positive, that's talking about the polarity of that bond, between carbon and oxygen. Well, it's possible that when you look at the electronegativity values of the two atoms, there's the electron cloud is not skewed one way or the other. A really good example is if you take something like oxygen. Of course, oxygen, diatomic element, right? So this is now this isn't the full Lewis structure, okay? But this is showing you that covalent bond between those two oxygen atoms. Remember we did these delta chi. What does delta chi mean? Change in electronegativity, yep. So remember we just kind of take the absolute value of the difference between the two Pauling or electronegativity values. So in this case, what's the electronegativity difference here? What's that? It is 0, yep. This is a case where we call this actually a non-polar covalent, because electrons are being shared, bond. Okay, this is what we would call a polar covalent bond. Make sense? Just for kicks, somebody help me out. Oh, no, you guys can't. How we can do this if we go back. I want to calculate the electronegativity difference here. I usually take the higher one minus the lower one. So what you're looking at, 3.5 minus 2.5. Okay, so that's kind of what we're looking at. Okay, so we have covalent bonds that are nonpolar too. Good example is where you have two atoms that are the same, like an O2 molecule. Or it's possible, I'm going to go back and get kind of dizzy, it's possible to choose two of these, because remember, it's the nonmetals, I get my metals and nonmetals mixed up sometimes, but it's the nonmetals when they're bonded together that will form covalent bonds. Electrons will be shared, not transferred. So you can pick any two of these, come back. You can pick any two of these, and it would be a nonpolar bond. Oh, here, carbon and sulfur. That makes sense? Okay. Polar covalent bond. Polar covalent. Polar meaning that there's an uneven kind of cloud of electrons, electronegativity difference. Covalent means electrons are still being shared, electrons haven't been transferred. This example of polar covalent bond. So the higher electronegative atom will be partially negative, and the other one will be partially positive. I think, okay, so we had electronegativity, you know what I mean, electronegativity difference of 1.0 here. I think in Chem 1 I talked about if that pushes about 1.7 or greater, that means that the one that's higher electronegative will actually abscond. I don't know if that's a real word, but it will actually take an electron. An electron will be transferred, and then now you have an anion and a cation, and then you're going to have an ionic bond between those. I think here in OpenStax that threshold's not 1.7, it's going to be 1.8, but it's kind of a similar thing. Okay. So it's covalent electronegativity difference is still not great enough to result in a complete transfer of electrons. Let's see if my thing writes. My thing, of course, being this. I don't think it's looking good. Let's see. Oh, yeah. Okay. So delta chi, I'm going to say greater than, I wonder if it's an angle thing. Yep, maybe so. Greater than 1 point, I'll stick with 1.7 or 1.8. Then I'm going to say, I'll say electrons transferred. Actually, I just wanted to write on my slide. Okay, polar covalent bond. Sometimes in chemistry or in science, I just kind of repeat the phrase. I'm like, oh, that's what that is. Polar covalent bond. So here we have kind of this little fuzz bit is kind of like this little fuzz bit that I had here, where think of that as kind of the electrons are being shared unequally over this right one. It's got more, must be higher electronegativity, right? And we're looking at the hydrogen. It's supposed to be the hydrogen. That's a chlorine. So here you see the lowercase delta. So that means partially. So partially negative, okay? Partially positive. Anytime you see that, like an S with an extra little tail, that's a lowercase 3-letter delta. Another good way to show polarity is this, okay? Where, and this is actually, you're going to see it more likely this way here in a minute than this way. But these two mean the same thing. This is the same thing as this. But notice, and it kind of makes sense, what we do is we draw a plus here, and it's kind of like in physics. The length of that arrow counts. Length is significant. So the longer the length, the more the difference in the electronegativity of those two. And it's also what we call a vector thing. It's got like a direction to it. So length is magnitude, and the direction of the arrow is significance. Okay, polarity of HCl. So again, this kind of reminds me of something we covered in Gen Chem 1 also. When you're looking at two atoms being bonded together, if their electronegativity difference, the delta chi, is 0, then what sort of bond will it be? Nonpolar. Yep. Nonpolar covalent. Yep. So nonpolar covalent. Nonpolar covalent, another name for nonpolar covalent is pure covalent. So anytime you see pure, think delta chi is equal to 0. Pure covalent. Electrons are shared equally. And it can happen. If the electronegativity difference exceeds what I say, 1.7 or 1.8, then electron's going to be transferred. And then the bond won't be covalent, the bond will be ionic. And then there's somewhere in between we get these covalent bonds where electrons are shared, but they're not shared equally, so polar covalent bonds. Notice that it's kind of what we call a continuum. Kind of, there's not a pure break sometimes, okay? So this is where I was telling you that OpenStax, this particular chemist who wrote this chapter went with a 1.8 instead of 1.7 criteria, where the electronegativity difference is great enough that the one with the higher electronegativity will take an electron. And now notice also, I thought this was interesting. Again, this is our first time to teach from OpenStax. And they say you can say something is basically nonpolar, pure covalent bond if your delta chi is less than 0.4. So that gives you some options. All right. This was actually from Chem 1. Again, it's kind of in degrees. We have this electronegativity difference, 1.7 or greater, electron transfer, your chemical bond won't be covalent, it'll be ionic. Nonpolar, that's pure covalent. We have some